is on using deep learning for classification of time series. So this is a very specific topic. It might be useful for some of you, especially postgrad students or anybody who is working on this topic. So I will try to simplify it as much as possible because we don't have enough time to cover a lot of theory. And I will focus more on the code walkthrough at the end. So actually, most of the tutorial will be indeed a tutorial. So we will walk through a code to show how to do that in practice. So again, the agenda for this first is just to introduce very briefly what's a time series, just to put everything on this in perspective, and we make sure that we are all on the same page, and what examples are used for applications of time series, and then we will jump into why we want to use the deep learning for classification of time series. Classification of time series is just one of the analysis methods for time series. Here we have to talk a little bit about deep learning, so we might briefly introduce the concept. I am assuming that some of you, because I know some of the students who attended are not specialized in computer science, they have little background about deep learning, so we might introduce this a little bit so that we can follow the rest of the discussion. Then we will see what's the concept of applying deep learning for signal classification, for time series classification. And most of the rest of the tutorial will be about code walkthroughs. So we'll take a couple of 3 examples from the applications of time series, specifically activity recognition and anomaly detection. These are very common applications. Many students I know, they have projects and they want to use this deep learning tool for classifying their time series. So first, what is time series? Time series, we all have some sense of that. Actually, from Wikipedia, a time series is a series of data points. So we have readings, some data points, these data points coming from measurements. And the condition for a data point set to be time series is that they are indexed in time order. So they are ordered in a sequence. So this is a sequence that is taken at successive equally spaced points in time. So there is an assumption here that the difference in time between each point and the next is fixed. So this is very regular readings, and they are ordered in time, and they could be anything actually. So this is a time series. And by definition, this sequence is discrete. So the index of time is usually discrete. So we discretize the time because we always measure that using some digital sensor, and we will have to discretize the time so that we have discrete readings at discrete time points. Examples of time series, for example, this is just incidence of some kind of disease in US, TB, over time. This is cases of COVID in the middle over time. And the last example is also over time reading from accelerometer, x-axis, y-axis, z-axis, that could be, for example, built in a smartphone. Some other examples, generally, you collect time series from sensors. These could be environmental sensors like climate measurements, for example, temperature, humidity, pressure, etc. Could be motion sensors. These are just few examples, by the way, like acceleration, vibration. Other positional sensors include gyroscope, etc. So these are readings taken over time, and they are usually regularly spaced in time. Sometimes the difference between each data point and the next one is measured in minutes, sometimes in hours, sometimes in weeks or months or years. Most of the motion sensors, you read them spaced in maybe milliseconds, sometimes a little bit microseconds. It is very rarely. Most of the time, it is milliseconds, especially for example, you could have maybe 100 accelerometer data per second. So if you have 100 readings per second, means that every 10 milliseconds, you take a reading. And medical sensors also used for collecting vital signs like blood pressure, like ECG signals, for example. Or the time series can be produced from transactions, human transactions, for example, stock indices, purchases over time, for example, or events and incidents like what we saw previously, incidents of disease or COVID-19 infections. These are just examples of the sources of time series. So traditionally, you could have many reasons to analyze time series. For example, you might be able to explore the data. You just want to explore. Why? Maybe you want to understand the temporal behavior. So the time series reflects some kind of behavior over time. This is called temporal with respect to time. So if you want to understand this, you have to analyze the time series. You maybe want to understand the underlying process, the process that produced this time series. So you want to produce a model that can reflect or that can represent the actual process that produced this time series. Or you just want to visualize this time series to communicate something to some other people. Another task is to estimate the past or the future. Future is most interesting. So many people talk about forecasting or talk about prediction. This is very common task. Our focus for today is classification task. Classification means you assign for a group of time series, just a subset of the time series, you assign some class, some category. So you just label some group of time series with some kind of label. Could be an activity, could be a condition of a machine, an activity of a human, a disease, for example. So this is the classification, which is the focus of this tutorial. One very special case of classification is the anomaly detection, where you classify only two cases, normal or abnormal. So this is very common and very used often. Actually, it's extensively used in manufacturing, in every kind of your intrusion detection, for network security, for disease detection, for equipment, for predictive analysis, etc. So the time series classification, specifically if we talk about TSC, time series classification, one definition from this paper, all the references are listed at the end. This is any classification problem that uses data which was registered taking into account some notion of ordering. So these are the definitions of time series. So if you classify some categories based on data ordered in time, this can be classified as a TSC problem, time series classification problem. Applications of time series classifications include human activity recognition, automated detection of heart and brain disease, failure detection for the purpose of predictive maintenance, for example. Anomaly detection, this includes a lot of things, includes stock market anomalies, network intrusion detection in cybersecurity, bank fraud, condition monitoring, machine fault detection, etc. So we will just assume that these are intuitive and many people have a sense of that. So we'll just move into the more hands-on aspect of the tutorial. So now let's go into deep learning. But before we talk about using deep learning for classification of time series, let's just step back a little bit. And you have to, I am not sure if you have some background in this kind of manipulating time series, but generally and very roughly on the surface, we can just divide the analysis of time series into very traditional methods. So traditionally, many people, especially statisticians, they have used a lot of techniques for analysis of time series. So there are a lot of techniques like autoregression, ARIMA, modeling, moving average. These are mostly used for modeling and prediction. And these are decades, it's very famous actually, it's very popular and it's used extensively daily. But for task size classification, this might not be efficient and it might not be effective sometimes. Actually, many times, especially with the nowadays, we have a lot of data and these data are complicated and usually we combine a lot of measurements together. So this is a simple example that shows that sometimes from a single machine like X, if you take X, this is a time series, could reflect anything, could be acceleration data, for example, and this is Y, another time series. So if you take two signals together, this is two aspects of a time series. Probably this is an x-axis, for example, y-axis of the same sensor. This is now called multidimensional time series. Sometimes it's called multivariate time series. So only looking at individual signals, you might not be able to discover a lot, or detect something like an outlier. Only when you combine these two signals together in somehow, then you can discover something. And sometimes these signals, the dimensions are more than 2, 3, 4, 5, or more. So, and the relationship between these variables are more complex and more complicated. So very traditional techniques might not be able to do that. Many of them are linear, by the way, so they cannot catch non-linear relationships. So if we talk about classification of time series, we could do just simple thing and without any kind of machine learning or deep learning. If, for example, just let me give you an example. If your signal looks like, just 1 minute, please. If your signal is just like this, for example, you just have a signal like this. And for example, these are easily distinct. For example, these readings over there can mean some, let's assume some high activity or maybe high temperature or whatever. So all of your readings are like this. It's very easy to just draw a threshold like what I did now. And then you can just compare every reading in the future or in the past or in the present with this threshold. So this is a simple task. This is very simple one, and it doesn't need any complicated or sophisticated manipulation because your readings are simple. So there is a natural distinction between two categories of the time series, two categories of the time series meanings. So for example, this could be high temperature, this could be low temperature, and the distinction between them is easy. So you just draw a threshold, you compare any reading with a threshold, and you just decide what class any point belongs to. But if it is not simple like this, take example, for example, this example, or a time series that is more stochastic something, or where the trend is not very straightforward, and or the trend is extending over long periods of time. So it might not be as easy as this case. So in that case, people they resort to the machine learning or deep learning. So deep learning is just a subset of machine learning. It's just a recent trend that we will see why we want to use deep learning over machine learning. Machine learning is adequate, it's very powerful. You use it when you cannot program a task, when you don't know exactly how to model a signal, how to detect some trend, for example, with the easy traditional techniques. Probably you just throw this at a machine using a machine learning algorithm, and you ask the machine to learn from the data. So that's the power of machine learning. It avoids you to program everything. If you don't know the rules, if you cannot dictate the rules explicitly, probably you can ask the machine learning algorithm to learn the rules from the data directly. So that's very powerful. But then we have also deep learning, and we'll talk a little bit about that. So just to elaborate on an example, the health of a complex piece of equipment as an example. It cannot be reliably judged based on the analysis of individual measurements. And so we need to combine a lot of measurements usually. And then the correlations, the relationships between these different signals, different measurements, different aspects of the same time series, it might not be very obvious. So you might not be even able to visualize it. So you need somebody to help. So the time series classification, actually nowadays, more prominently using supervised machine learning. So using machine learning, as we said, if it is not very simple case, so you can use machine learning. And the most successful applications of machine learning are called, the one type of machine learning called supervised machine learning. This is the most successful type of machine learning currently in business, in manufacturing, in many fields, including classification of time series. So supervised machine learning algorithms, they analyze multiple labeled classes of time series. So you have a time series. I assume that, for example, some patterns here indicate something. You call this a class. And maybe another pattern like this one, for example, it indicates something else. So this is another class. Maybe this indicates normal condition, a hard condition. Maybe this indicates some abnormal condition for some vital sign from body, or maybe it indicates some kind of activity if this signal is generated by a moving object like a human, and this is indicating another kind of activity. So these are different classes. So if you have multiple classes, usually you have to label these classes. That's why this kind of machine learning is called supervised. Supervised because you label means you assign each pattern a class. So you have to tell the algorithm what is the class of each pattern. So then you feed a lot of data and you teach it. That's the supervision here. You teach it. You tell the machine learning algorithm that, look, this kind of pattern of signals is mapped to this label, this class. Another one is assigned to another label, and another pattern is corresponding to another label. So you label all the possible patterns you have in your signal, and then you feed a lot of data, a lot of samples. This is called examples or samples in the literature of machine learning. So you give the algorithm that is responsible for teaching the machine the patterns, the rules. You give a lot of examples or samples, including the patterns, example series, and the class, the corresponding class. And a lot of these, and hopefully the machine learning algorithm will be able to teach the machine. When I say teach the machine, means it produces a model. Model is just a name for a software entity, which is just a collection of numbers only. This is just really that. Think about the model as a big matrix or an array, multidimensional array, a lot of numbers called parameters. In the context of neural network, one of the most powerful machine learning algorithm, this is called numbers. And who will specify these numbers? The algorithm that is teaching the machine. And how it is teaching the machine? By looking at a lot of samples and trying to deduce, to guess some kind of rules, relationship underlying the relationship between these different patterns and its class. So the approaches for machine learning in classifying time series, there are many of them. So it can be distance-based, using, for example, k nearest neighbor algorithm. This is one machine learning algorithm, or based on that, or with this is another distance-based algorithm called dynamic time window, or dynamic time wrapping, which is used with this KNN algorithm, or could be just discovering some shapes within the signals. So this is called shapelet based algorithms, or could be just model ensembles. So this is using a lot of machine learning algorithms called ensemble. Ensemble is a group of machine learning algorithms, then maybe voting or combining their classifications, and then coming with a single classification at the end. This is one of the most popular considered state-of-the-art algorithm, Hive code, in classification of time series using traditional machine learning, or could be dictionary based like Rocket, or could be interval based like time series forest, etc. So we don't care about that, actually. It's just to complete the picture. So you just be aware that traditionally there are a lot of techniques for analysis of time series. If you come to the classification, there are already a lot of techniques to classify time series using machine learning techniques, including these approaches. But what we are interested here is use deep learning for classification of time series. So if we talk about that, we have to notice that many methods for time series classification, we just reviewed some of them in the previous slide. They first use some algorithm for measuring the difference between time series that you want to classify. For example, the DTW. They just try to come up with some what is called a feature vector. So, sorry, this feature vector means some kind of a way of signals or indicators that you can use later on to specify the class. So maybe these indicators could be used, could be maybe by, for example, measuring the distance between a time series and another kind of time series, could be the difference between a time series and the shape you know about the time series, could be using some other statistical kind of analysis, including all those techniques here. And then after that, what you do after you have uh, generated some kind of features, then you can move and apply one kind of classifier like machine learning algorithm, KNN, SVM, neural network, etc. What's the problem with this? It is okay, it's powerful, everything is fine, but there is one thing common between all of these approaches. They all require some kind of feature engineering. This is the key word here. So actually, the key reason, after all, why we want to move into deep learning from machine learning is just to avoid this feature engineering. Feature engineering means you have to do some manual work to extract features, to extract some indicators from the time series that will help you. So actually, you don't take the raw time series as is. You have to manipulate the time series somehow. Imagine you have a lot of data points along the time, so a lot of time points here, and a lot of individual readings. A lot of it. If this is acceleration, we are talking about a few readings per second, or could be 50 readings per second, tens of readings per second. So maybe every few milliseconds you have a reading. So there are a lot of points, and you cannot just give a single point as a sample. We talked about samples. It's very difficult to learn anything from this a single point. It's very difficult. What could you discover anything from just a point hanging there? Okay, it is corresponding to a point in time. That's it. But it could be any value. It's just a stochastic random value. So what to guess from that? What to learn from that? It's very difficult to learn from that. Also, there are so many of them. So usually you don't take just raw points. Usually you group the points together. You take groups. This is usually called windowing. So you take a window of readings, and then you try to summarize. You come up with a summary of this group of signals, of this group of points, data points, readings, actually. So kind of summary. Actually, you don't come with one summary. You come up with many summaries. So this is called features. So probably, for example, if I take this window, there are a lot of readings here, maybe 50 readings, maybe 10, maybe 100. Then what I do with them, I extract a lot of summaries, kind of indicators that will help me to know what class this window belongs to. And these are called features. For example, very common features in the case of time series could be the minimum value, the minimum reading, the maximum reading, the mean, the average, the standard deviation, the skewness, etc. And people actually are creative in extracting these features. For example, some works in the literature, you can find that one paper can derive more than 100 features, a lot of statistical measurements. They extract this from each window of signals. So this is very tedious and time consuming. And not only that, it depends on the expertise. So if you don't know the domain very well, you don't know what's the meaning, the underlying meaning of this signal, it's very difficult to come up with a feature that really reflects what kind of activity is going there. So if you don't understand the physical phenomena, for example, that is producing this signal, it's very difficult to think of a feature that is representative of the class of each pattern of the signal. So that's why it's tedious. We want to avoid this if possible. And here comes the deep learning, actually. The power of the deep learning is that it eliminates this stage of feature engineering. So feature engineering includes feature extraction, derivation of these summaries, and feature selection. So sometimes you have a lot of features already there, and you just try to analyze the features, and you extract or you select some of them, the most representative features of what you want to do. And this is called feature selection. Feature selection and feature extraction is collectively called feature engineering. But what we want to do, we want to use just kind of deep learning. And research has shown actually in many other domains like computer vision, natural language processing, is that really it's very powerful to just jump into deep learning because you don't need to use feature engineering. So actually, the meaning of that is that you can throw the raw data to the algorithm that is teaching the machine, so learning algorithm, and then the algorithm will learn the features instead of you, on behalf of you. So it will look for features, it will detect, so you will use feature detectors, it will detect the features from the raw data, and you will use this in a hierarchy of layers. This is called layer. Maybe you will have a look at this later on. But the algorithm somehow will be able to discover the features and distinguish between different characteristics of the raw data on multiple stages, multiple layers. So, for example, it can discover high-level features, detailed features, and it will have a wealth of features discovered by itself, which will allow the algorithm easily to just assign this sample of signals to a class. So they will understand what this group of signals belong to, what class they belong to, just from the raw data, because they will look into features themselves, the algorithms, and they can come out with the exact class, or maybe approximately the exact class, because the feature they discover are very detailed on multiple levels, which is probably very difficult for you to come up with yourself without expertise in the domain and without a lot of time. So if we build on the success of deep learning on computer vision, NLP, and we try to do the same for time series, and people did that already, then you can use deep learning for time series classification. Now, let me just, I am not sure, I know actually some of the students I know personally, so I know they know nothing about deep learning. So that's why my talk is a little bit high level, abstract. But let me just very quickly introduce this basic concept of deep learning. So when I say deep learning, I am referring to a subset of machine learning. So the traditional machine learning algorithms include something called neural network. And if the neural network is large enough, because neural networks usually are arranged in layers of neurons, this is neural network. So if a traditional neural network is composed of only one or two layers of neurons, these are the nodes called neurons. So these are nodes. Then if you arrange so many layers, more than 2, 3, 4, sometimes could be tens, or more than 100 layers. So you can refer to this neural network now as a deep neural network. And this is deep learning. So deep learning is specifically referring to using neural networks of so many layers. So it excludes all other algorithms from the traditional machine learning. It's only neural network, and it's not shallow neural network. It is a deep neural network with so many layers. The essence of this neural network, no need to know the details now, no time, but the essence of this, that this model, which comprise a lot of weights, you can see these edges. There are edges connecting the nodes. So these are representing numbers. So these edges are just numbers. These are called parameters or weights in the context of neural networks. So these numbers are receiving the input values. This is a raw data. Could be a pixels of an image, could be, for example, the volume, the signal coming from a voice, or for example, data points coming from acceleration data, etc. So then they pass through multiple layers. At each layer, they are multiplied by the weights, and then this multiplication is a linear process, and they are added. Then at each node, they will undergo some nonlinear function. This is called activation function. And then this will be repeated many times. So you will take the data. You can have multiple features here. You can have many, for example, in a case of acceleration, you can have many axes, X and Y and Z, and you can even combine group of readings together. Then you multiply each one with a weight, and you add these together. And then you apply some kind of a function. Most of the time, the function look like this. This is called a ReLU, or could look like this. But the point is, it's a nonlinear function. The details are outside the scope of this talk. This is not about deep learning or machine learning. But the point is, we can capture in this way non-linearity between in the relationships between the different variables, between the different inputs here. So somehow, this is the magic of neural network, magic of deep learning and machine learning. Somehow, the final result will be what we want. So if we teach the neural network enough with enough samples, and we allow the algorithm, the learning algorithm to adjust these weights, to change the parameters until it reaches a point where whenever you produce, you feed some input, and it is multiplied many times with parameters from layer to a next layer, and undergo a lot of activation functions many times. So somehow the final result will be the correct. For example, in case of classification, you can specify one class out of two or more classes that this pattern belongs to, the input. Machine learning is not used only for classification. We can use it for regression, for example, if you want just to receive a series of points and we want to just predict the next point in this series. But this is outside the scope of this talk. So the power of machine learning, again, I talked about this previously, is that instead of specifying the rules, you don't know the rules. If you know the rules, don't use machine learning. If you know that, of course, if this reading, for example, is above this threshold, then this is the class. If it is below that threshold, then that is the class. You know the rule. So you just provide the data and the rule and do just simple, C program or Python program or Java program, and you can specify the class. But if you cannot dictate the rules, then you just use a machine learning, and the machine learning will deduce the rules for you. So that's the main point about machine learning. You multiply the weights by the input. Here, the point is in time series classification is that instead of taking, for example, pixel of an image or some features, for example, signals of from a body of a patient, which are just independent of each other, they don't relate in time to each other. Now we take group of readings in a time series. So time series which are related in time, we take group of them and we feed that here. And then we just pass this through the neural network, and the magic of neural network will do the job. We can do that in using this. By the way, it has a name. This is called Perceptron in the neural network literature. And if you have many layers of this perceptron, this is called multi-layer perceptrons. And then people didn't just take this classic architecture of a neural network. Just you take perceptrons and you arrange them in layers, and you just then stack layers after each other. People actually customed the architectures of neurons based on the application. For example, probably you have seen that. This is called CNN, Convolutional Neural Network. And what happens here is that now the neurons are doing something else. It's arranged somehow in another way. So now the arrangement of the neurons are in groups called filters. So these filters are convoluted with the image. For example, this is the input data, and you will use, and each group of these neurons will be called the filter. So sometimes when you people talk about feature maps. So when you convolute a filter, actually the filter is a small one, small window. When you convolute convolved a small filter with the whole image, and somehow it's not the topic of this tutorial anyway. So then what happens, you produce another big image or small image, it depends on how you do, could be the same size, and the resulting image or resulting matrix is called a feature map. Then you use many filters and you do the same many times, so you include many features maps. Then you move the feature map through other filters and repeat the process again and again. Sometimes you down sample, sometimes using something called pooling. But eventually, to perform the classification produced by this kind of neural network, you just convert everything to this kind, which is called the dense neural network. Dense means every neuron, every node in this layer is connected to every neuron in the next layer. So this is a dense connection. It's dense because everything is connected to everything else. So eventually you will come up to this dense shape, dense format, and then you will use the same magic you have used before to come up with the class after all. So now I am assuming that we are convinced that maybe we can use this deep learning approach for classification. How can we do that? I will just refer to a few examples from the papers and from tutorials online, or the references are at the end. So uh, I encourage everyone interested in this, especially the students that I know who are working on this time series classification, to refer to this paper. Actually, this is a review paper about time series classification using deep learning. That could be the title of the paper, by the way. So they have classified TSC, time series classification, into many techniques. So all the techniques, they have classified this in a taxonomy. Um, but most importantly, I will take some of these examples, actually a couple of these examples. So one way is called generative models. This model try to first represent the data, model the data somehow, then after that perform the classification. I will take just an example from one tutorial about autoencoders. This is one kind of deep learning neural networks. We will take an example of that. We will show you the example. And I will take another example from end-to-end using discriminative models, which is just taking the raw data and trying to guess from this from the start to the end, what are the features, then extract the class. So this is using multi-layer perceptrons and convolution neural network. So we will refer to one-dimensional convolution neural network, because all these examples you have seen before is called this convolution layer is called two-dimensional convolution neural network, or convolution layer. But we will use, if we have a time series, it is we will assume that it's one-dimensional. So we use one-dimensional convolution layers. And this is general. This is taken from the same paper, by the way. This is a general unified framework for time series classification. So you have to understand this to be able to apply that in your project. I am talking specifically now to my students who are working on this kind of problems. So now you take these signals. If you have many signals, okay, if you have only one, this is called univariate. If you have many, it's called multivariate time series. But all of them, you take a group of them, okay, and then you apply, you feed this to some kind of nonlinear transformations, which is the job, which is the business of the convolutions of the neural network, the deep neural network. So the deep neural network is no more than some nonlinear transformations. And eventually after that, from these transformations, you will come up with a lot of features. Then you can use just some kind of dense layer, and you classify. You come up with a probability distribution of the classes. So if you have 3 classes, you assign a probability to each class, saying that, okay, I think, for example, 80% that this group of signals belong to the activity of A, and maybe I think that maybe 10% or 15% that this sample of signals, these are all considered one sample, by the way. This is not the whole data set, because usually you have a lot of data points. So you have a whole data set, which can include a lot of data readings, could span weeks or months or years. But here we are taking only a sample by sample. This is how neural networks work. So a sample in this case is one or multiple dimensional signals, a group of signals. So it's not only many, 1 or 2 or 3 signal, maybe X axis and Y axis and Z axis of the accelerometer data, but also you take many points. This is X axis of acceleration. This is Y axis, for example. This is Z axis. So you take three, but also you take group of readings. You don't take only single data point. It's useless. You take group of reading, a window. If you remember from our previous slide, this is called the window. So you take a window of these readings, 1 or 2. It depends, univariate or multivariate. So you reshape this and you feed into the neural network, and then you classify. This is the general framework. So this is another picture that illustrates the same concept. You have multivariate time series here, group of signals, 1 or 2 or 3, some window. In this case, it is multi-dimension. Then you pass this through the layers of the neural network until the end. This is another one using 2-dimensional neural network. So you can use 2-dimensional or 1-dimensional. If you want to see how 1-dimensional neural network, maybe you can refer to this. This is an example of 1-dimensional convolution, where you have a signal here. You have, this is the filter we talked about. So if you have 2-dimensional signal, the filter that convolves, means it performs convolution, will move along the image, the 2-dimensional space here. But if you have only 1 dimension, then your filter will move just in 1 dimension. So the filter will move, this is the filter in this case, it will just move down the 1-dimensional signals. So using, this is 1-dimensional convolution, but you can use also, this is 2-dimensional convolution. Later on, you can refer to the details. Or you can just use an MLP. Of course, it could be deep, but for example, these signals, X, Y, and Z, they are different classes. These are reflecting human activity like walking, jogging, sitting, etc. So you can use this is a layer of a multi-layer perceptrons. So you can feed these signals into these nodes, and then you can pass these through multiple layers, and eventually you can classify this using the normal dense layer classification. There will be some activation functions here that are capable of producing probabilities to each class. This is called soft. But anyway, we will not talk about the details. And this is a very simple way of doing this 1-dimensional convolution for a series. So this is a time passes from top to bottom. So you have a series of readings. In this case, the time series of length n and width k. So you have many samples, each one, for example, in this case, could be X and Y and Z, etc. And you will have many of these, like 10 readings, 50 readings. You don't take single reading. You don't take single point. And then you convolve a filter. Convolution means you just multiply each value, each weight in the filter by the corresponding number inside the input matrix, and then you add up the result and you put it here. So this is like a sum of products, and you will pass in one filter, you will pass through all the from top to bottom, every, for example, sample here, every like time point, you will pass through it, and you will take 2 rows and you will multiply and add, then you will produce a single value. And then while you pass down, you will produce many values. So this will be in one dimension. This is a feature map, one feature map, but you can use many filters actually. So you don't have to use just a single filter like that with some set of weights. You can use multiple filters. And you can do the same multiple times. So you can use the second filter, third filter, fourth filter, you doing the same convolution with the whole sample of signals, sample of time series of length n and with k. This is considered one sample, one example. And then you will produce many feature maps. Then you will flatten this afterwards, and you will feed it to a normal fully connected layer or dense layer, and you will do the classification. So this is roughly how you apply deep learning for time series classification. So it's the same deep learning used everywhere. Could be a multi-layer perceptron like this one, or could be convolution like this one, but eventually is the same. Is the same. Just the input will be a custom time series. It's not individual pixels. It's not features of some kind of object or some kind of event, but it is the data points coming from a time series. You arrange them, you take group of readings, and you might have one univariate or many of them. You might have example. It's okay. You can classify this temperature indicating the machine is not good or the machine is okay. Or you can have multiple dimensions like temperature and humidity and vibration. These are all one in one data point, one time point taken at the same time. So these are multi-dimension. Or in the case of acceleration, could be x and y and or z axes of the accelerator. So you take this and you take a group of signals. That's why we have this matrix. And then you feed that into one or two, in this case, one dimensional convolution. You set a filter, you move the filter from the top to the bottom or left to the right. And then you do the convolution, you produce individual values, you stack them in feature maps, then you can apply, and then you just use a standard deep learning model. So let's move now. I know we have lost more than half an hour, sorry for that, but let's move now into code walkthrough. So I will refer to what I'm doing now is that I will try to run walk through a few tutorials. I already referred my students to these tutorials, but I will list them again in the reference lists. So one tutorial is about using machine learning for anomaly detection. I know this is a very common problem, and many people are interested in this. So this is used for condition monitoring of, in this case, it is using data set from NASA bearing, some readings from bearings, and for the purpose of monitoring the condition of the bearing. So in one experiment, they just run one machine until the bearing are just failed, just have failed. And they collected a lot of data from these vibrations of the bearings. And then the task here is to just predict when the bearing is about to fail. So in this tutorial, the author is using two techniques. One is based on statistical analysis. Actually, it is using also one kind of machine learning algorithm called PCA, principal component analysis. And another one, these are the readings collected from the bearings, from 4 bearings. And another technique is using autoencoders. This is also another kind of deep neural networks. And let me just show you the final result. So this is the desired result. These are the time points, and derived from the readings of the bearings, the motion of the bearings. They derive some kind of distances using first PCA. PCA is a technique for, this is called principal component analysis, to reduce the dimensions of the data and just extract the most important components of the data. So then they can draw a threshold, and they can tell whenever the readings is above, the readings here is after manipulation, after transformation. So this is actually some kind of distance measure. So if the readings, the transferred readings are above the threshold, then they can tell that the bearing is not normal and is about to fail. And this happened also for the autoencoders. They repeat the same for autoencoders, which is based on neural networks. And this will be the result the same again. So in the case of autoencoders, actually the manipulation is that the autoencoders is a spatial neural network. I didn't talk about that, sorry, but in autoencoder, usually you feed the data to some kind of layers, and these layers, these nodes, try to understand the data and try to reduce the dimension of this data and somehow compress all this data into a representation, which will be here, probably using less nodes. And finally, the data will come out later on at the output. So this is the input, this is the output. Some magic is happening here, but then the output here should be representing the same data, same input data, but in a reduced format, maybe compressed. So it should reconstruct. Here, reconstruction happens here. So the reconstruction should be close to the original data, but if you look at the middle, you will find that the data are reduced. This is compressed somehow. But it represents the features of this input data. So then at the final output, this final output layer will reconstruct the signal from the compressed version, and it should be close to the input, means the most important features should be representative enough to reconstruct the original input. So now if you manage to take the inputs and somehow generate some kind of features that represent this input in a reduced format, then you could reconstruct again. So what's the purpose here? How you can find anomalies? Maybe you can look for the differences, the errors in the reconstruction. So if the errors in the reconstruction is too much, this could be anomaly. If the error of the reconstruction is acceptable within a threshold, this could be a normal condition. Because after reconstruction, you will have some error, difference from the original. So if the difference is too much, this is indicating you are feeding afterwards, after the neural network has already learned the reduced format. So it learned how you should reconstruct. So in the normal condition, it knows how to reconstruct. So it should reconstruct without errors, without much errors. But if you bring some new reading and the neural network tried to reconstruct, but the difference was too much above some threshold, then maybe we can classify that new reading as an anomaly, as something abnormal, not normal. So again, the purpose is to construct is to establish some kind of model that can reconstruct the signal. So based on the normal data, I know how to reconstruct the signal. So if you bring me normal data, I will be able to reconstruct the signal. So there will be some error, but I know what are the acceptable ranges of error. I know it. I know from the training process. If you bring some data point, a new sample, and I apply the same model and apply the same reconstruction, and then I found that I get something at the output, when I calculate the error, that I know how to calculate that, and I see that this calculated signal is now above some threshold, I will just classify that new signal or new sample as an anomaly. This is generally the idea, but the details can be seen from this tutorial or from the code. So I will just reproduce the code very quickly, walk through the code, and we can refer to this later on. But how I can run the code, you can use you can install all the required libraries using Python language, and we are using some libraries like Pandas, NumPy. These are Python libraries, and some machine learning frameworks like scikit-learn and TensorFlow and Keras in this case, in these examples. So these are the names of tools used, software tools used to help you in applying machine learning and deep learning algorithms. So these are very common tools. Of course, I cannot explain all of this now, but I hope that some of you have the background. If not, maybe you can refer to this independently, but at least you will know how to apply this from this very short tutorial. So you can install that on your PC, or you can use something, a cloud service or some online service like something called Google Colab, for example. So Google Colab is using something called Jupyter Notebooks, and I am using the same here locally. So I just run something called Jupyter Notebook, which is the same that you can find in cloud service. If you don't want to install that in your PC, it's okay. You just refer to something called Google Colab. So you can refer to that. You can use that online without installing anything on your PC, or you can also install that on your PC if you want. So the first example is referring to this tutorial. I'm opening a specific file. This is called a notebook, Python, Jupyter Notebook. This is one special file. The format of this file allows you to write both code and text also. So you can mark up your code. You can include the code and the results of running the code. So usually when we say that we have Jupyter Notebook, this is actually installing kind of server. This is called kernels that can receive the code from this file, which is just a web interface, and then can run this code for you in the kernel and return the results and write the results on the interface, on the web interface, on this page. So these are all the codes taken from this tutorial. Again, the idea first is you use principal component analysis, PCA. But before that, typically what you do, typically in any task, you first, I hope that you can see this enough. Yeah. So typically for Python programming, you start by importing the libraries you need. So now they are available in memory. So you just, and then you start always with reading the data. So always refer to, you have to look first at your data. The data is all the collected data points. In this case, this tutorial is referring to a specific data set provided by NASA. And this data set looks like a lot of files, and each file includes a lot of readings. So each file includes a reading of maybe 10 minutes, I think. So, and it is just a collection of readings, probably it is XYZ and something else. No, these are maybe the 4 bearings, if I am not mistaken. And then the name of the file, it includes the actual data point. So actually, this is very strange arrangement, but the label of the time point is actually the name of the file. So this is the group. I told you usually you take a window, these are the windows. So these are already arranged in separate files. So you can consider each one is a window. So you can actually take one reading out of this window, and then you can even group many of these files. Actually, what the tutorial is doing is that takes one summary of this first window, one summary, maybe the mean, the absolute mean, and then they group 80 or 40 or they group some of these files as a one sample. They feed that to the neural network. So they read the file here, and they use something called pandas. Pandas is a library of Python. It can arrange the data, load the data into a shape of a table, so something similar to Excel. And then they do some manipulations. For example, in this case, they merge. They take the name. They take, for example, as I told you, they take many files, and they take the mean of the absolute of a file, so a single file value from each file. Then they just add that value to some kind of we call it data frame, some kind of data structure called merge data. So now after this, they will have a table of data, many rows like these. And if you notice, actually, there are some differences. So there are differences of 10 minutes. So they have taken one number from each 10 minutes. And then now they have a lot of samples already. They will just manipulate, they change the time and date, so it is something understandable by the rest of the program without much details. And then they will save this data in a single file. So this file will be here, in this case. They produce this merge data bearing. This is the result. So they have combined 4 columns from many different files. So from each file, they have taken one line. This is a sample of the data, how it looks like, 4 readings for the 4 bearings. And the label, the time label is this, used to be the title of the file. And then they split the data usually, as usual, they split the data into 2 sets, one for training and one for testing. So they just select from one day to another day. They take few, maybe 2 weeks, and they reserve the rest for the testing data. And this is just a plot that shows you sample how, this is from the training set, how they look like. So they take few samples here. And this is how the bearing readings look like, bearing 1, 2, 3, and 4. Then the next step is just to normalize, means you cannot just take these values. This is not proper for the consumption of the neural network. Any kind of machine learning, actually, they are using PCA here, but still for PCA or else. So they assume some kind of normalization. In this case, they are using a function from the scikit-learn pre-processing this library here. So there are already ready functions you can use. You can apply kind of manipulations, transformations, including this kind of transformation, which is normalization. So these are the dataset, training dataset. They generate some kind of transformation for the normalization, and then they apply the same for the data for the test dataset. So this is just roughly. And also they shuffle the dataset so that it is randomly. The samples are random each time, so you don't memorize even the order of the data points. And here they apply again. They just import something from a library, scikit-learn. This is already, the algorithm is already programmed there. You can just apply it. So they apply the PCA algorithm. So this is how they apply it: PCA fit transform for the X train, and then they extract actually some features actually from the X train. This feature later on, they will these are the normal data. Training data is the normal data. By the way, I forgot to mention that this data set is arranged so that in the beginning, in the first part of the data, the normal. But in the last part of the data, the condition is abnormal. Why? Because the experiment was like that. It was running the machine until the bearings fail. So first period will be normal readings, normal, normal, normal. At some point, it will start, it will start producing some abnormal behavior until it fails. So if you go to the final portion of the data, this will be indicative of the abnormal condition until total failure. So that's why they have taken the first part of the data for training, because they want, the idea here is that they want to train the algorithm for the normal condition. Then they will produce distribution, probabilistic distribution for the normal condition. And whenever they receive something else, some new, they will compare this with the distribution. If it is far away, it is coming far away from the normal distribution from where it should be, from the expected value, then they will say, okay, that could be abnormal. So that's the general idea. The details are hidden in the code and also explained a little bit roughly here. But generally, I want just to show the students that it's possible sometimes, even without understanding the underlying details, whether the machine learning details or even the analysis details, to apply the code and to get the results. So these are very typical after they apply the PCA using this fit transform function. So then they store the training after transformation into a pandas data frame after transformation. And they do the same for the test. And then they combine both of these. And they calculate something called covariance matrix. Covariance matrix is just because they need that for an algorithm called Mahalanobis. Pronounced Mahalanobis distance measure. So this is a kind of an algorithm that can measure the distance between two distributions. So it needs covariance matrix, or this is a ready function. So when you use Mahalanobis distribution distance measure, you just provide this matrix. You calculate it from here, and the mean distribution of the normal data and the actual data you want to classify, you want to calculate the distances for. And after you get the distance, you are comparing with a threshold, and you decide whether this is an outlier or not. So it's mostly statistical analysis. The only thing that is machine learning is the PCA. So if you run all these, but the point about this is very fast. So actually, these are already run. Of course, you can always run the. If I want to run, I have to go from the start. You run. I am clicking Shift and Enter. I am running all this code now. Running indicated by the star. So I am running the code, and the result will be stored in memory. And if there is something to display, it will be displayed in the same file. So all these have been run previously, but I am not running it again. But because my laptop is very slow, as you can see, it takes time even for importing some libraries. But anyway, you should just remember that the code is available. The idea, the general idea, is mostly about comparing distribution with new value, new data points. You build a distribution for the normal values, and this distribution is based on some representation of the data coming from the PCA. So this now is reading the data. There are a lot, you can see the data is read. There are a lot of data points. So this is, by the way, not CNN. This is a machine learning, but it is used by this tutorial, and it is effective. So if you have something similar, something like readings of something, and you want to discover where is the failure point, then you can use this kind of algorithm. Okay, it will take a lot of time. Actually, my laptop is very slow. So now I'm generating the figures again. Applying the transformation, applying the PCA. Here is the core of the thing, the PCA. Then just defining the functions that we will use later on. These are functions used. These are all mathematics, by the way. So here you apply everything. Here you give the training data, PCA values of the data for the training set and data set. Here you calculate the covariance matrix using a function above. Here you produce the mean of the normal data, because you need that. You need that for calculating the distance using this Mahalanobis distance measure. And then you can have a look at how it looks like. This is how this is showing, plotting the distance of the training, this one, which is the distances from the mean of the, so this is a distribution of the normal distances, Mahalanobis distances from the mean of the normal data. So usually the distances are 0 or close to 0. If something is very far away, means this is not good. So after establishing this, you can calculate the threshold, and you can build a distribution for the Mahalanobis distribution. It look like. So maybe you can establish from here. After you calculated this distance, and it is above 3.5, for example, in this case, it says 3.8. Then probably this is starting to fail. The bearing that I am reading its vibrations right now. And these are all visualizations. So here I am showing they are combining all the data in one table, in one data frame, just to be able, and concatenating this, just to be able to draw it together, the normal and the abnormal. The result is that indeed it seems that the algorithm and the determined threshold are able, actually the endpoint by the definition of the data set is the failure point. So we could detect that there is something wrong 3 days before. So few days before it fails, you could say that something is wrong because the readings, the distances you measure are above the threshold. So that's the idea. If the distances you get are above the threshold, you can specify that please pay attention. Probably you have to do some maintenance. For the autoencoder is kind of deep learning, so it uses neural networks. And for neural networks, we can use Keras. Keras is one kind of this is an API library. So Keras, you can build neural network. So how to build neural network? You just stack layers together. You use some dense layers here because this is autoencoders. Autoencoders, I didn't explain that, but it is what I drew previously. It's just some layer, then fewer nodes in the subsequent layers. Then at the end, the output will be the same dimension as the input layer. So here we have dense layers, and okay, you just add the layers one after the next without going into much details. But you can just run this code, and you can compile the means. You can just prepare the model. And when you prepare the model in machine learning, usually you choose some kind of measure for the loss function. In this case, it's mean square error. And you use some kind of optimizer. Optimizer is the thing that will do the learning. So this is the optimizer that will optimize adjust the weights until the weights are okay. So there is something called the number of iterations. You don't pass the samples through the network once. You do that many times. It's called epochs. And also you don't pass one sample. Sometimes you pass many samples together. This is called batch. or in this case, each sample is already many signals, and you will pass 10 samples together. So this is how usually you do machine learning, deep learning, especially. It will take a lot of time, but here it is very fast. So each epoch takes a little bit of time. At the end, we have reached already 100 epochs. So, and we get something like a very, very small loss. So then this is a visualization of how the training went. And this is showing the loss decreasing with the epochs. And this is a distribution of the normal. And this is a test showing that many of these are normal. False means it's not abnormal. And this is finally visualizing the threshold using autoencoders. It's very, very similar to the PCA. So all this code will be provided later on. This is ready to run. And this code is applying anomaly detection using two techniques from this tutorial. The first one. So from how to use machine learning for anomaly detection and condition monitoring. So you can apply this for anomaly detection if you have a time series from some kind of machine. Okay. And there are two techniques here already, PCA and autoencoder. There is another tutorial. I give this one to another student, actually, can be used by anybody who has similar problem. This tutorial is about human activity recognition from acceleration data. So you have acceleration data and you want to guess the human activity. Is it walking? Is it jogging? Is it sitting, etc.? So in this case, all these activities, this is a classification. And you can use many kind of, deep learning. You can use multi-layer perceptrons. You can use one-dimensional convolution neural network, and you will see both. So we'll see first how to use multi-layer perceptron, and then one-dimensional convolution network for this purpose. Actually, if you are one student also has a similar problem where she wants to classify not the activity of the human, but the condition of the road. So there is a very popular problem called road condition monitoring. So if you have, if you want to monitor the condition of the road, so the roads means the streets. The condition is, for example, you have smooth roads, you have speed bumps, you have potholes, you have cracks in the road. So you can use acceleration data, of course, fixed in the car, and you can collect data with labels. Of course, you have to first collect enough training data, and then maybe you can classify the road condition, same like you collect data from the human while walking, jogging, and you label the data. And then later on, you can measure the acceleration, and you can tell whether that person is walking or jogging or running, etc. So there are two techniques here. First, using just deep neural network. By the way, the data set here is coming from some website. They have collected a lot of data. Actually, the samples are near 1 million, more than 1 million. And the attributes are 6, means they have, the classes are 6, but they have many attributes because they are taking the acceleration and something else, probably. Let's have a look. This is how the raw data for the acceleration look like. So this is the number of the person, and this is the class, and this is the timestamp, and these are 3 axes, X, Y, and Z. So in total, there are 6 attributes. So these are the most important, X and Y and Z. These are acceleration coming from 3 axes of the accelerometer. So this is how the data look like. And this, what is this tutorial is doing? First, it is applying a deep neural network, multi-layer perceptron, MLP, to the data set. And just that, no features now, nothing. It's just you select every, for example, here, maybe you select, okay, you select, for example, 80 of these window, okay, a window, and you have 3 features. You don't care about this. You have 3 features, X and Y and Z, and you group 80, for example, together, and this is one sample, and you just feed it to the neural network, feed it to the multi-layer perceptron, or feed it to the one-dimensional convolution neural network, and that's it. And that's the magic. Then you apply this standard code, very standard code. It looks complicated now, but it's actually, if you are used to see this kind of manipulations, you will see that it is quite straightforward. Then you will get the result. You will get the class without even feature engineering. Otherwise, you will have to do a lot of feature engineering. You have to summarize the data. You have to extract a lot of meanings. So now let's see how it looks like. It's using a very standard libraries again. And there are explanations here, but because there is a shortage of time, I will not go through all these explanations here. I will leave this for you later on, but I will go very quickly through the code, giving you the rough idea. Because here the code is straightforward. It's not like PCA previously here when we talked. There is an idea behind PCA. There are distributions, idea behind autoencoders. Here it is a black box. You just prepare the data. Here, for example, you select 80 readings, and you step through them. For example, every 80 readings, you step through this, and you provide 80 samples to the neural network. You build a neural network. Building a neural network is straightforward using Keras. I will show you where. This is the main point here. All those codes is preparation. And by the way, most of the time spent by machine learning engineers and data scientists is just doing data preparation. Applying actually this is how to build a neural network. That's it. You can see 11 lines. That is building a neural network in Keras. This is one of the API libraries. So you can build a whole neural network in this number of lines, just 11 lines of code, and that's it. So building the neural network itself is not the problem. The problem is what kind of manipulations, what kind of preparation you need. So if you refer to this code, it's very simple. Then you just do, if you remember from the previous, you have a compile and you have a fit. This is called building the model. This is called training the model. You have to wait until it's trained, then you can visualize and you can test. You can do this after this manipulation. You can do this using MLP. This is just a normal multi-layer perceptron, or you can use it using one-dimensional CNN. First, let's look at the DNN, the multi-layer perceptron deep neural network. So again, it's just importing some data, some libraries, sorry. And after that, reading the data. So in this case, they just prepare the labels because they want to use it. And they have some time periods, means how many readings they will take from the data. Every 80 reading, they will take 80 readings together. You can also overlap between different segments if you want. So if you take a group of signals window after window, you can also overlap between these windows if you want, or you can make them distinct. This is the function to read the data. Let me just, okay, finish. So this is just defining something. This is the function to read the data. Again, it will refer to a file, and it will use something from pandas called read CSV. Of course, there is no time now to go. This is not a tutorial about pandas or NumPy, but just to show the students, especially the students who are working on that it's possible to use the code. Okay. Later on, if you want to go into depth, you can study the pandas, different functions like read CSV. These are already built-in functions. You can just use them. That's the power of using libraries nowadays. And then in this case, they do some manipulation. So for example, they prepare the different columns. If there is something they don't want to use, they replace it like a semicolon. And then they apply some transformation like converting to float, etc., which is just producing a float number. I want to remove this. So now I will run this block of code. This is Jupyter Notebooks allows you to just execute every block of, this is called a cell. So you execute a cell and you get the result. And now you have a look at the data, how they look like. This is how they look like, but you can see that the values are still, usually the values are normalized, means we move the data into a range from 0 to 1. These values are not appropriate. We don't like that there are much difference between the different ranges of values for different variables. So this is how to do. Later on, we will do some kind of standardization. But before that, this is just visualizing the data. So this is how many walking, how many jogging samples you have. And this is different people with different kind of readings. These are functions to plot the data. So if you plot the data, it will look like this. This is just taking some samples from the file. And now you produce the labels. Actually, you are coming up with a column called activity, and this will specify the class for each kind of samples. You take some for the testing and some for the training. So you divide it into some persons. Below person number 28, you will take it for training, and the rest, the sensor reading coming from those persons from 28 and above, you will use for testing. And this is just to do basic normalization, moving the values into the range from 0 to 1. Let me just. And then this is how you build the different samples. So you move through the file, and then you produce something like 80. This one, let me just show you. It is first a long series of data. Later on, maybe if you read that, you can understand. So it is just a long series of data, long table. And you have 3, X, Y, and Z, and you have some time. Now they produce some, they take 80 of these. So they put it in one row. So they build a table, a new table, where they have these rows. But actually, each row here is actually 80 sampled together. And here, the columns are the same. You have 3 columns. The point is that one segment is now 80. To get this will be one sample. So you will give this at once to the neural network, not a single line, not a single time reading. No, not a single reading. Every 80 readings from the original file, you will take as one sample. That's where they do this this kind of segmentation. So create segments and labels. So they move and they take a label and they take group of samples, group of readings. Actually, this is time steps, and they put it into the segment, and they add segments all one after the other, the X and the Y and the Z. So everyone, they take a number of samples from the X, number of samples equal, number of samples from the Y, number of samples from the Z column, and they then concatenate this in one row. So this is now a single sample. Anyway, the details are not very much important, but after all, from these segments, they will produce the training dataset. So this will be the training dataset. Let us just execute this. And this is just to confirm how much data we have. Because if you do that, you will have this kind 20,000 lines, samples. Each one is actually 80 multiplied by 3. So each sample is 80 by 3. This is one sample. And how many samples you have? More than 20,000 samples for the training. So these are the labels. Then here, instead of 83, because they have multi-layer perceptron, something like this we have seen here. This multi-layer perceptron is an array, one-dimensional array. So instead of having 80 by 3, they convert it into 240. So 80 multiplied by 3, they just flatten this one. They concatenate all these together in one line. So now they have 240 actually. So there will be many samples, 20,000. and each sample is 240 number will be fed into the neural network.
Sorry, Doctor. Is the 80 the layer?
The 80, no, the 80 is the one sample. So the layers, no, the layers will be more. I will show you the layers now.
Okay, okay.
But these are not the these
What
are
is
the
80?
sample, the input data, the input.
Input.
So the input, this is the first layer, the input layer, isn't it? Then you have many layers. So this is the first layer, okay, the input layer, where it is connected.
Oh, okay, okay.
So you bring one sample, will be flattened to 240 from here to here.
240. Okay.
240 will fed into the first layer, then will come to the next layers, and we will build the layers together. You will build the layers. So
okay.
I know it is difficult to absorb all the details from here. That's exact. But I want actually, I am addressing my students. Hopefully later on we can discuss this more. But at least they know that it is possible. And the code is available. So just rest assured the code is available. You can always refer to the code. So here we build the network. You see, these are the layers. First layer, the input layer, will be time periods 80 multiplied by 3, which is 240. And then we build next layer, dense layer, 100, 100. This will be 3 more layers, hidden layers, 100, 100, 100 nodes each. Then the last one is flattened. So there will be 1, 2, 3, 4, 5. Actually, these are the layers. So this is the first one, 80 by 3. And then this is another layer, 100 node, another layer, 100 node, another layer, 100 node. And finally, the last layer, 8,000. And the output layer will be 6 categories. These are the categories, the classes. So building the neural network is just using Keras to add these layers. Of course, the details are left for other for later on, because you have, of course, to read, or maybe we can talk about that in a separate tutorial. But just to show the general flow. So now we have built the neural network. We have now to train the neural network using fit. This fit function is doing the training. So if you do the training, you will find this is going through a process. For example, in this case, we are using 50 epoch. So 50 times we will go through all process. But we are using something called early stopping. So if there is no improvement, we can stop. But otherwise, if there is an improvement, means the loss is decreasing and the accuracy is increasing. This is the accuracy of the training data, but we have something called accuracy of the validation data. This is the people who will understand this, only the people who read about machine learning. Because usually when we measure the performance of the neural network, for example, we use 2 sets, the training and something called validation, validation set. And we measure the accuracy for this and that. And we hope that the accuracy of the validation will be close to the accuracy of the training, hopefully. And you see now the training is, the neural network is performing the training, means now the optimizer, the algorithm, some algorithm is adjusting the weights until hopefully at some point the classification will be as much accurate as possible. So this will continue until we finish 50 rounds, 50 epochs, or there will be no improvement in the loss, because here the specification that if the loss is not improving after one, from one to the next, then you just stop. So maybe it will stop at some time. If this loss is not improving, if it is the same from one to a next one, it might stop. It might stop and not continue to train until the 50 epoch. But as long as there is an improvement, the loss is decreasing. Hopefully, the accuracy is increasing. And by the way, this algorithm, this neural network that I built, it's not efficient. It's not the best. But even the tutorial author said the purpose here is not to make it optimal, because you can play with all of these. You can play with the number of nodes. You can play with the number of layers. You can play with the batch size. You can play with the epochs. You can try different combinations, and you might get better results. But in this case, he got something above 70%, which is good. So this training will continue until there is no improvement or the epochs are 50. Then after that, we can test it. We will get something like that. This figure shows you how the training was going on. So in this case, we have a red line, solid line for the accuracy of the training data. Usually, always the training data will be good. The accuracy of the training will be good because we are telling the neural network what's the correct answer. So neural network is seeing the answer and it is just adjusting itself. But the validation, for the validation accuracy of validation data, this is the blue solid line, it will be less than the accuracy of the training data. But these are not what concerns us. We care about the testing data. We have testing data other than this training and validation data. We care about that. We hope that the performance of that data will be good. So if we continue doing that, it stopped already at 25 because there was no improvement. Probably, yeah, it's 28 here, 27 less. So the loss stopped to decrease. It's coming back to 28, 0.28 after 0.27. So it will stop here. So now the training have finished. What is the result of the training? A set of weights. Now the sets have already been settled. So we can visualize what happened during the training. This is what happened during the training. And we can also print something called confusion matrix. So these are all matrices, metrics. These are all measurements used to measure the performance of the neural network, of the MLP. So the total all accuracy here was 87%, which is good. Okay, given that we didn't do any tweaking, any optimization, just we throw some standard layers stacked with each other. These are different metrics. I will not explain these here, but these are used for each group, each category, walking, jogging. So probably you don't care only about the accuracy. Sometimes it's accurate overall, but you care about something else. For example, in the precision, you care about if you correctly classify something as the correct class, how percent of the time you, for example, this is usually referring to within the group of the walking, for example, how much percentage of the walking you detected. So this is referring to only for was you correct how many percent of the time you said this is walking. Okay, it was walking many of the times it was walking, but you missed some, and you means whenever you said walking, how much of the time it was actually walking. It's a little bit subtle, but that's the general usually people refer to this with respect to false positive and false negative. So precision refers to if you are saying that this is positive, for example, some class is positive, or you are detecting some class. So what percentage of the positive you have discovered? So are you far away or are you close? But recall means how much percentage you detected in the first place. So did you detect all of the walking, or half of the walking, or quarter of the walking? Precision is when you say walking, was that how many percent of the time is what actually walking? Maybe you didn't detect all the walkings. Maybe you detected only 10% of the walkings, but within that 10%, how much you were correct. So it is a little bit subtle difference, but there are differences. Sometimes these differences matters. So sometimes you want to know not only the overall accuracy, but also the different measures. And this metric is just combining these two. But this is actually the topic for another talk. But let's move on and see for the testing how it will do. So for testing, it's okay, 75%. That's the actual measure. Actually, this is representing the actual performance of our model in the production when you use that for new data. And these are just other visualization. For example, in this case, it is using the confusion matrix to get insight into which classes are easy to classify, which classes are not easy. For example, you can see that jogging and walking are good. Most of the time, when it says, when the true label was jogging, we actually said jogging. Our model said, yeah, it is jogging. But and we saw the walking is the same. And it is expected because most of the samples, if you can see from here, most of the samples are for walking and jogging. So we have enough samples. But let's look at, for example, this upstairs. When it is upstairs, sometimes you say it is downstairs. Sometimes you say it is jogging. Sometimes you say it's upstairs, yeah. Sometimes you say it's walking. So there is a confusion, a lot of confusion here. Means there is a weak point here in classifying the upstairs and some other classes. So that's the one. I will stop here because this is the one. Let's just run another example. I will not run it, but because it will take time, but I will show you the result. So this is another example, the same problem, human activity recognition. You can use, again, this for road condition monitoring, exactly the same. So in this case, you are just using convolution network. So all the manipulation is the same. You read the data, you concatenate the columns, you standardize the readings, etc. It's always all the same until this point, until building the neural network. So in this case, previously, when we built the neural network, it was just dense layers, let me check. It was dense layers. It was just traditional machine learning, traditional neural network layer, just dense, fully connected layers. But now the difference is we are using one-dimensional convolution layers. So conv1D is a ready-made layer from Keras. You can just use it, and you can just stack them up. It's same, 240, 80 multiplied by 3. Then the first layer is 100 filter. Sorry, 100 filter. Each filter is 10. This is referring to this. I said, for example, here you use filter. You can use more than one filter. What's the width of this? This the width of this filter. The height is 2, but it could be 10, for example. And you can use many filters. So you produce 1, 2, 3, 4 feature maps. So this is the number of filters. In this case, we are using 100 filter. Yeah, you usually use big numbers because you want your performance to be high. So you here we are using 100 filter. Each filter is 10 in width, in height, and this is activation function. The more details, but you stack many layers, including pooling layers and dropout layers. I didn't talk about that, but at the end you use a dense layer, and then the classification will happen here. So this is the layers. These are the layers, and then here we do the training again. The training will go like this. It will the loss will decrease, the accuracy will increase. Eventually we will get something like 96%, very good accuracy using one layer, one dimensional convolution layer. This is training. What about testing? Testing is 91%, still good. This is testing data. And this is the confusion matrix. So that's it. So this is using human activity recognition. You can use also road condition monitoring and similar things. Reading from acceleration data, XYZ, and you can guess whatever you want. You can apply the same exact neural networks, but just change the data file. Just change the data file. So I have also other example, but I'll stop here. So that's enough. We have also example from Ford Motor engine noise. Same, is just engine noise. You just specify whether it is noisy or not, means whether it is normal or abnormal. Again, we have here same code, same, again, the core is here. You build, this is building more larger neural network, but the same again, just add layers after layers, and then you train using fit, and then you go through the training, and then you test. In this case, the testing is very good. It's 97% for the test, and this is how the training went. It was good, so the accuracy was increasing over time. So sorry guys, we talk a lot of time. I will stop here. So I will provide you with this slide later on. I know some of you will be interested in this. I know that not everybody is interested in this. And sorry that for the hiccup that we started more than half an hour late. That's why we took a lot of time. Actually, I joined more than half an hour late because of my laptop problem. So eventually what I will do, I will share with you this slide. So, and also I will share with you the code. So anybody who is interested in the code, they can refer to especially if you have a project, you want to apply the same techniques for whatever problem you have. I know already some of my students, they have this problem, anomaly detection, so they can apply the same concept here, PCA or autoencoders, for detecting, for example, the bearing failure of some kind, or any other measurement of equipment, really. Other students, they have this human activity recognition or road condition classification, etc. So they can use this kind of, you have two examples here, for one-dimensional convolution neural network or for the MLP, deep neural network. And there is also this kind of engine noise, the noise from the engine, classifying it is normal or abnormal. All these codes can be applied to different data sets. If you are interested in this, you have some projects, you can refer to me. I can provide this code through Ahmed. Maybe later on we send this or we put it somewhere and we email. The slides also will be available. Hopefully later on, this was just a quick tour as a quick tutorial. Hopefully, if there are many students who are interested, many people who are interested in this, we can specify, because every month we have two tutorials. Actually, we have 2 sessions every month. So we can dedicate some sessions to more details. If you are interested in the details of the deep learning, we can focus on the deep learning. If you are interested in the code, Python code, we can dedicate some sessions to this Python code. So we appreciate your feedback. And again, I apologize deeply for everybody of you, everyone. And thank you very much for your attention and bearing with me until this time, which is very late. Thank you very much. So I'm not sure if there is any quick question. Maybe we can take some question, but I appreciate and I respect your time. So if you are already fed up, please feel free to leave us now and join later on in our next sessions. Thank you, everyone.
Thank you, Dr.
Okay,
I have
welcome.
a question.
Yeah, Ahmed, please.
How do you know like certain problem is suitable for certain method?
Okay, very good question. Yeah. Actually, yeah, first, you know, because you learn about machine learning types of tasks. This is called tasks. So machine learning are capable of solving different kind of problems. One of them is, like we said, for example, one of the famous tasks is to do, for example, something called regression. Regression is coming from the statistical world, where you try to predict the next data points in some distribution. So you have some readings, and there could be a trend among these readings, and you want to predict the next readings. You want to predict some kind of individual readings. So usually you predict some value, which is a number. And this value number could be a continuous number. And usually in statistics, what they do, they try to fit a line through this trend. So they look at the data and they try to explore the trend, and they try to fit a line. Most of the time, if it is linear regression, the trend can be the data can be, you can fit the line like this through the data that is close to as many points as possible. So this is representing the trend of the data. So in this case, this line is now a model that models this distribution of your data. And then if you have any, you want to predict, for example, any value from this axis, given this axis, for example, could be the prices of a house given the number of bedrooms, could be, for example, the number of sales given the season, or could be, for example, the grade of students given number of hours they have studied, etc. So following this line, you can probably predict what will be the new the reading for the new x-axis, what will be the corresponding y-axis from the x-axis, because you are following this linear model. This is one kind of regression, but regression can maybe the fitting the line. Sometimes you fit the straight line. Sometimes the data is like this, so you cannot use a linear model. You want something non-linear. But another kind, this is regression. So a regression means you come up with a prediction. You come up with a single value that is a prediction of a future, for example. And many times you want to classify. This is called classification. This is another kind of tasks. So sometimes you have regression, like, for example, I give an example. If you understand what is regression, then you can relate to your problem. Many students here in UNITEN, they have a problem of, for example, predicting what's the value of the power produced by a photovoltaic, for example, panel, for example, given a temperature. So if this is a temperature or some other variable, it could be only one or two. Sometimes it's not only two-dimensional the data. Sometimes it's many-dimensional. You cannot draw it. But they want just a regression problem because they want to just to know the expected power output of the cell or of the panel. Okay, so this is a regression problem. So you look for the regression algorithms. So you have linear regression. You have you have different techniques to do regression. Neural network can be used to do regression. There are different algorithms that can use regression. Even SVM can do regression. You have linear some algorithms, they can do regression, but you just understand that your technique, your problem is regression, so you use the corresponding technique. Because you want a single value. You want to predict something, like you want to predict the climate change. You want to predict the temperature in the next month. This is regression. You want to predict the power. This is regression. You want to predict the price. This is regression. Or sometimes you want to classify. So your problem is like what we talked about today. All of our tutorial today is about classification. I have readings, and I want to know these readings from accelerometer. It indicates walking or jogging or sitting or driving. These are different classes. So now the output is not a value, continuous a number, continuous value. It's just a categorical. It's a category. It's one of very limited number of categories. So it's one of two. This is called binary classification. Maybe it's normal or abnormal. This is like anomaly detection. If this traffic of the network is normal or it is abnormal. So for example, in security, many people are studying intrusion detection system. In intrusion detection systems, what they do exactly, they measure the traffic from the network. The packets means the packets coming in the and out of the network, and they know already what the normal traffic looks like. So they can just classify between two classes, which is normal or abnormal. This abnormal, sometimes we can call it an attack. An attack because we are talking about network security. So it might, we assume that indicates an attack. Of course, it can indicate just some misuse of the network or some malfunctioning of a hardware. But normally, it can indicate an attack. We are interested in detecting attacks. This is binary classification. I have two classes, only two categories. But I have also, I can extend this to many classes. Sometimes your problem is no. Tell me what kind of abnormality, what kind of attack. So maybe you have 3, 4, 5, 10 or more different kind of attacks. So I have first normal, this is only one class. And then the first attack is another class. The second attack is a third class, and then so and forth. So this is still classification. So I can use what I use today, like MLP, convolution, and SVM. A lot of algorithms are doing classification. Sometimes I have, these are all supervised. This means that you already have data that are labeled. So you know, you have already examples. So you know, for example, in this temperature, what is the power? You have a lot of samples. In that temperature, that was the power. In that temperature, that was the power. So I have a lot of examples that are labeled. I already know the answer. So I use supervised learning to do regression or supervised learning to do the classification. If you don't know anything about the, you don't know the labels of your data, means you have data, means you have, for example, data about users, okay, about customers. But you don't know, for example, you have purchases of customers. But really, you don't have an idea about how many classes you have or how to classify your customer. You don't know the answer, actually. You don't know how even to classify them. Means you classify them based on what? Based on their ages, or based on, is there any pattern among them? Is there any kind of purchases special for certain group of the customers, but that you don't know. So this is another task called clustering. There are algorithms that can look at the data and can group the data into different clusters, different groups. And maybe by this, you can discover some patterns, some common characteristics between different groups, and then you can treat each group differently. And this will be useful in different. And there are other tasks. There are other tasks. Anomaly dimensionality reduction, like PCA, is another task. Also, sometimes you want to use unsupervised learning for visualization. You want to reduce the dimensions to just visualize, or you reduce the dimension to compress. So if you know the available types of machine learning and what's the nature of tasks then they know what to choose. You map to your problem. So for today, what we did, we say if you have anomaly detection, so you have a lot of series, data series, time series, we call this, and just to discover when is something is abnormal anomaly. This is classification, because I have two classes and can use different approaches. One approach is just to feed it into neural network, but there is more creativity. In the first tutorial we have seen, they are creative. They use PCA to produce some kind of representation of the data, and they compared each new value to a threshold. So this is kind of creative, but it's the same. Is I know already how the normal data look like, so this is supervised. I train my model for the normal data, so that whenever there is an abnormal, it can detect that. And we also use autoencoders. Autoencoders, same. They represent the data somehow, so that they know how to reconstruct the normal data. So whenever there is an abnormal data, it will not fit the reconstruct. The error of reconstruction will be too much. So you can use this again. Autoencoder is just neural network. Again, the purpose is classification of anomaly detection, but indirectly. It is using some creative way. But more direct is the second tutorial we talked about, like using MLP, using CNN. Is very direct, is very typical classification problem. You provide the raw data as is, you don't do anything. You don't calculate any distributions, you don't calculate any distances. You just throw the raw data to the network and it will do the classification for you. But if you have different, like this problem, like the people about, photovoltaic, power prediction, this is regression. This is not classification. So if you want to classify what class of power, is it high, low, something else. By the way, many people are looking at the fault detection. Many projects in UNITEN also about fault detection. So again, fault detection, some of them use images. So this will be used using convolution neural network. But what's the appropriate technique for that? What this problem is exactly? Is it regression or classification or what? This is classification, because you have images, you train the network for different kind of faults, different kind of defects, different images. So you see the panel, if it is have this problem, this will be the image, look like that. And you use 2 or 3 kinds of defects, 2 kinds of problems, 3, 4, 5. These are different classes. And then you train your neural network for detecting each defect or each class. This is classification. If you want to predict again the power or the temperature or the next price, something, this is regression, etc. I hope I didn't take too much time, but is it okay, Ahmed? Did that answer your question?
Yes.
So the conclusion is you have to read about the machine learning types, so that then you can relate to your problems.
Yeah, true. Okay, thank you very much, Dr.
Okay, welcome. Okay, we are already 5 o'clock. Yeah. I really appreciate that you are bearing with us here. I am embarrassed already by the time we have lost at the beginning, but really thank you for sticking around. And again, I hope I will see you in the next session. Please provide any feedback if you want specific topics. But again, I repeat, for this particular topic, we can reiterate on this with the students who are working on this project. So we can, for my students, I will hold with them other meetings. But for others who are interested, they can communicate with us.
I think I can upload this what do you call it? The slides.
Yeah, I will send this to you. Then you
on the
can
Facebook.
send it through the what? Facebook
And just,
or
yeah, put it on the
yeah,
Facebook.
Facebook. Energy Sphere Facebook.
Yeah, and just share Facebook too.
Okay, guys. Anything else? Any addition, correction, or any clarification? A quick one.
For now, no question, Doctor.
Okay, I know maybe you are overwhelmed, but it's okay. I know if many people they don't have enough background about deep learning, this will be too much. So it's but again, the purpose is just to show the feasibility of these things. So the general approach and the resources, most important, the resources. So at least you know how to solve your problem, where to work on your project. Later on, you can elaborate on more details. Okay, guys, because really it's very difficult to deliver in 1.5 hours, for example, a wide topic like that, because you see this title includes many different concepts. We have time series, we have classification, we have deep learning. And when you study deep learning, you have to go through the machine learning. And it's a long story. So there are a lot of details. And in this tutorial, we have looked at the code. And this is another story by itself. So you have to be aware of, you have to look through some Python code, what different libraries are used, etc. So this is overwhelming, I know, but at least you have a sense, you have a taste of these kind of tasks. So if you have a project, at least you know what resources you will need. What's the general flow? What's the general flow? This is very important because many times it's not about the details. Many times you don't know even the approach. You don't know even how to start. So you don't know even the general overarching approach that we will take. What's the approach to solve this problem? So I hope that this tutorial have just delivered that only. Just give you an idea about what kind of techniques can you use, how much code you will use, and what's the general terminology and the concepts you need to study, and details can come later. If that's
Okay,
happened,
Doctor.
I'm okay.
Kindly,
Okay, Muhammad, thank you very much.
okay,
Yep.
kindly share the slides for
Yeah. We will send this, Ahmed. We will upload this to the Facebook page of the Energy Sphere. Okay, so.
Okay, appreciate it.
Okay, thank you very much. Okay, guys, I think.
Thank you.
Okay, if nothing else, maybe we can call it a day. Again, I repeat, thank you again. Apologies for.
Thank you, Doctor.
Sessions.
Yeah, thank you very much, Doctor.
Okay, thank you, everyone.
Thank you, everyone.
Okay. Assalamu alaikum and good evening now. So see you later, inshallah.
Wa alaikum salam and
Thank you.
Ramadan Kareem, inshallah.
Okay, for you too. Thank you.